So the last thing that we did was we were talking about colored compounds related to transition metals. And we had started talking about the colors of complexes and what are complex ions and how are they formed. So I told you that if copper sulfate or any transition metal salt dissolves, the ions dissociate, they scatter. The ionic compound, the positive and negative ions, if you stir vigorously the ions, they would mix in water or any solvent. And you would have all these water molecules coming in. There would be a copper 2 plus, and the lone pairs on the water molecules, which are your ligands, they're going to get attracted to the copper 2 plus and they would start to surround it. And six water molecules are usually going to completely surround the copper ions, and it's going to have a 2 plus charge overall. And this complex ion that is formed is going to be blue in color, and it was called an octahedral complex. Why? Because there were six water molecules that were getting attached. We also figured out, how do we figure out how many ligands get attached. The answer for that was that smaller ligands, which are smaller in size, for example 17, 18 MRs, they're smaller in size, so you have six of them getting attached. If you have bigger ligands, then you're going to run out of three-dimensional space. So if Cl lines, because they're bigger in size, their MR, the AR is bigger. It's twice the size of the MR of water molecule or an NH3 molecule. So in that case, you would have not a lot of Cl lines would get to surround this copper. And copper with chloride ions, Cl minus one ions. This is the complex that's going to be formed, and it's yellow in color. And but it would appear greenish because of the presence of this complex as well, which is blue in color. As anyways, there were certain complexes that you had to remember. Their structure, their shape, etc. Everything. Copper with NH3 is pretty much the same. Uh, like a water ligand, NH3 is a similar ligand. It has lone pairs, and they're going to get attracted. And this was deep blue in color. And the number of NH3, because NH3 usually is aqueous, so there would be water molecules present as well. So because of the presence of water molecules, uh, they could be, I mean, the total number of ligands would be six, but they could be one water molecule and five NH3 molecules, of three NH3 molecules and three water molecules. So the number, so it's not always that all of them would be NH3s. They could be water as well. So then I told you about this complex ion that if you add sodium hydroxide, it has OH minus one. The OH minus one ions are going to come and they're going to replace the water molecules, and copper hydroxide is going to be formed. Cu with two OH ions, and that's a pale blue precipitate. And you had to remember the colors of the cobalt complexes as well. They had the same shape. They were pretty much the same complexes as we discussed with copper. The only difference was that they had different colors. So you had to remember the colors of these complexes as well. Now we're going to move towards another thing which is called ligand exchange. I said now, related to ligand exchange, you're going to get very specific questions on ligand exchange. And let me quickly explain what is ligand exchange first. I said, so I have this copper complex with six water molecules. This is copper 2 plus. In the middle, the overall charge on this entire complex ion is going to be 2 plus because water is neutral. Now, ligand exchange is that if in this solution, in this aqueous solution, if I start adding any other ligand, for example, if I start adding NH3 ligands and there are lots and lots of NH3, I'm adding NH3 in excess, and lots of NH3 molecules come into the solution. Then there are going to be obvious collisions. And if NH3 concentration increases, the water molecules might get knocked out. And in their place, you would get these NH3s that would bring in their lone pairs. And they're going to substitute the water molecules, which were previously attached to, to the copper ion. Now, this copper ion, these dative bonds that are formed over here, they're not permanent dative bonds. They're not very strong dative bonds. Most of the time, they're very weak because I told you that copper has more protons, so it has this tendency to attract electrons. But the thing is that it's not a non-metal. It doesn't have so many protons, that it starts to permanently attract those electrons, and strongly, it doesn't really strongly attracts electrons, it weakly attracts electrons. So the lone pairs uh, are going to be pulled towards copper because of the greater number of protons, but not very strongly. So these water molecules, they can get knocked out if you introduce another ligand into the system. So this water molecule might get knocked out, and NH3 might take take position somewhere around the copper ion. So this is basically ligand exchange. Now we're going to talk about ligand exchange, and we're going to talk about some very specific reactions of ligand exchange. There were some tests for copper that were done in AS practical for identification of copper 2 plus ions. So there were two tests, and we're going to explain what happens in those tests using ligand exchange, the concept of ligand exchange. One of the tests for ligand exchange was that you add NaOH. For example, you have copper sulfate aqueous, and you add NaOH to copper sulfate aqueous. What you're going to get is you're going to get a blue precipitate would be formed, or a pale blue precipitate would be formed. So pale blue PPT forms, and this PPT is insoluble, which is insoluble in excess. So which is insoluble in excess. So if you add NaOH to copper sulfate aqueous, a pale blue precipitate forms, which is going to be insoluble in excess. So I have to explain what's going on over here. Now, initially you have copper sulfate, which is aqueous. So they're going to ask you about the explanation for this. So initially you have copper sulfate aqueous. Uh, so in that copper sulfate aqueous, the complex ion that's formed is copper with 6 water molecules. An octahedral complex of copper would be formed, and the complex is going to have a charge of it's going to have a charge of 2 plus. Now, when you add NaOH, what ligand is introduced by NaOH into the mixture? OH ions are added because of NaOH. So there are going to be OH ions coming in with their lone pairs, and those OH ions are going to knock out. They're going to knock out the water molecules that are previously surrounding the copper. So this thing would be produced copper with OH twice and 4 water molecules, and this entire thing is going to be neutral because copper is 2 plus and OH is minus 1. So copper is 2 plus, OH is minus 1. So the overall charge on this entire thing is going to be 0. And the 2 water molecules would get knocked out. Remember, it's a reversible reaction. So I'm going to balance this. This is my blue solution. And this over here is the pale blue precipitate that ends up forming as a result of this ligand exchange. Now the question is, why are only 2 OH ions substituting the water molecules? I can go back to this example. Why do only 2 OH ions? I'm going to rub off the NH3 molecules, and instead I'm going to bring in the OH ions. So these water molecules are getting knocked out by OH ions. So there's going to be an OH ion over here, and there's going to be an OH ion over here. Now the main issue with this is that once the water molecules they get substituted by OH ions, the charge on the overall complex it starts to change. Previously, like initially, if it was 2 plus, the overall charge on this entire thing was 2 plus when there were no OH ions. Because copper 2 plus tha, and the water molecules were neutral. But once the OH ions came in, copper is 2 plus and the OH ions are negative, the charge changes to 0. When it changes to 0, even if there are more OH ions around copper, the negative ions are not going to be attracted to this neutral complex ion. So the chances of further collisions decreases. And even after that, if there's another OH ion that comes in and is able to substitute one of the water molecules, now you have 3 OH ions and 1 copper 2 plus. So the overall charge becomes minus 1. Now there's going to be even more repulsion because of the negative charge. The OH ions would get repelled back. because the overall complex ion now has a negative charge. So further OH ions would be almost impossible now. And even the OH ions that are already sticking to it, they would get repelled because of the negative charge and they'll get knocked out. And water would take their place back again. So the thing is that you can't really get more than two OH ions to substitute the water molecules in this particular case because of the charge that's building up on the entire complex ion. So at the end of the day, the most probable complex ion that's formed is copper with two OH ions and four water molecules. So you have to write this explanation that this is what happens when NaOH is added to copper sulfate when you're testing for copper ions and why a pale blue precipitate forms. Now there was another test, and that test was with ammonia. And the test was what happens with ammonia. Add a few drops of NH3. That was the first part. That you add a few drops of NH3 aqueous, and what would happen is that a pale blue precipitate, so NH3 aqueous, 2 copper sulfate aqueous, and a pale blue precipitate forms. But then, when NH3 is added in excess, so when NH3 is added in excess, what then happens is when NH3 is added in excess, the pale blue precipitate dissolves and gives a deep blue solution. So it ends up giving a deep blue solution. Now the thing with now you have to explain what's happening over here. So you add a few drops of NH3 to aqueous to copper sulfate aqueous, and a pale blue precipitate forms. Now what happens is that when NH3 is added, initially NH3 acts as a base. When a few drops of NH3 are added, initially NH3 added, or more specifically, initially when a few drops of NH3 are added, so initially NH3 acts as a base. What that basically means is that because you're adding so little NH3, just a few drops, they're going to react with the water that's in the solution. And they start reacting with the water, and NH3 is a base. So it gains the H plus 1 ions from the water, resulting in the formation of OH ions. What happens is, if you remember the structure of NH3, NH3 is a trigonal pyramidal structure, and it has lone pairs at the top. So if there's a water molecule that's coming in, the water molecule is polar. It has an H, which is partial positive. The partial positive H, the oxygens have these lone pairs negatively charged, and this H is positive. So this H over here is going to get attracted to, because it's positive, it's going to get attracted to the lone pairs on N. And that will result in the formation of a dative bond over here. And the H would get a plus one charge because it lost its electrons. The electrons were left behind because the lone pairs would repel the electrons in this bond over here, and you would get OH minus one and an NH4 plus one ion. So this equation is the result of this reaction that happens when NH3 reacts with a water molecule. Okay, so this over here is the overall reaction that happens initially. So the thing is that even by adding a few drops of NH3, you're getting the same ligand. It's OH minus one that is being produced. So you get pretty much the same reaction as the first one, the one that we did earlier. You're going to get exactly the same reaction because adding NH3. So I'm going to write the first reaction again. It's going to be Cu with 6 water molecules, and they have a charge of 2 plus. And instead of NH3 having any role, the OH ions are going to come in and they're going to displace the water molecules, forming the pale blue precipitate of copper hydroxide with 4 water molecules, and the 2 water molecules are going to get substituted, and we can balance this equation. So the blue solution results in the formation of a pale blue precipitate. It results in the formation of a pale blue PBT because of the addition of NH3. But then what happens when NH3 is added in excess? Now, when NH3 is added in excess, what then happens is that particular NH3, because now it's in excess, now you're adding a lot of NH3. Now this would start happening that when you add a lot of NH3, now if you look at the complex, there's going to be, I mean, you're adding too much NH3. Okay, so there's lots and lots of NH3 coming in. Now the obvious thing that's going to happen is because NH3 is a ligand, so its lone pairs, the NH3 molecules, they're going to knock out the water molecules and they're going to take their place. And now NH3 starts substituting around the copper 2 plus. So when NH3 is added in excess, when you add a very large amount of NH3, this pale blue precipitate that was formed, copper with the 2 OH ions, and 4 water molecules, this pale blue precipitate, the NH3 molecules are coming in and they're going to start knocking out these other ligands. And chances are that if you add too much NH3, all of them are going to get knocked out, and all 6 ligands around copper would be NH3 ligands, and the 2 OH ions and the 4 water molecules would be knocked out. Uh, but this is usually not the case. What could also happen is, what usually happens is that you get a mixture of ligands. I mean, there would be N NH3 molecules and there would be 6 minus N H2O molecules with a charge of 2 plus. So there could be 5 NH3s and 1 water molecule around it. There could be 4 NH3s and 2 water molecules around it. So any number of combinations are possible if you keep on adding NH3 into the solution. This over here results in the formation of a deep blue solution. So and this is pretty much what the explanation for this entire statement is. That if they ask you to tell what's happening, then the first step is that initially NH3 doesn't act as a ligand, it acts as a base, instead reacts with water and ends up producing this pale blue precipitate. Because OH ions, these ligands are formed. And when added in excess, it starts behaving as a ligand. So it starts to behave as a ligand. So you must remember these two reactions. And there's one more ligand exchange that we need to do, and that is with the concentrated HCl, and that involves copper as well. So the question that you're going to get is, as a with copper, when concentrated HCl is added to, so when concentrated HCl is added to copper sulfate aqueous, a blue solution, it slowly changes to, when you're adding concentrated HCl, it changes to a greenish yellow. So it starts to change into a greenish yellow solution. So there's a color change that's happening. So I have to explain what's happening in the reaction. So initially it's copper sulfate aqueous. So it's copper with 6 water molecules. and the overall charge is 2 plus. You bring in this HCl, that brings in the Cl minus 1 ligand. And these Cl minus 1 ligands, they start substituting the water molecules. Cl minus 1, remember, is a bigger ligand. So you can only have 4 of them around copper. And the charge would be 2 minus now because copper is 2 plus, Cl is minus 1. Plus, there would be 6 water molecules that would get knocked out from the complex. And this is your yellow colored complex. This is your blue colored complex. The reason it appears greenish yellow is that blue and yellow, the combination would turn out to be green instead of yellow or blue. So I'm going to sum this up. This is all about ligand exchange. That you're going to have three different. I mean, you should have the ability to describe what's happening. You need to know the equations of these ligand exchange. The other thing is, uh, everything is going to be the same. This above, everything about it is going to be the same for cobalt. So everything is going to be the same for cobalt. Difference, the only difference is that cobalt has different colors. So you just have to substitute copper and put cobalt in its place. The only difference is that the colors of the complexes are going to be different. The colors have already been described over here. So cobalt with water is going to be pink in color. Cobalt with it's going to be a green precipitate. Cobalt with chloride is blue in color. Cobalt with NH3 is brown in color. So that is the only difference that you have to remember. Otherwise, it's going to be the same for cobalt, the same explanation, the same equations, but the colors are different. Now we're going to try and answer the main question that we had. Why are these compounds colored in the first place? I mean, you have lots and lots of compounds, and all of them have different colors. All of the complex ions have different colors. So the issue is, why are they colored? Now, there a couple of points that I need to make before we can go deeply into the explanation why transition metal compounds are colored. The first thing is about the about what colors are, and um, I'm going to draw the atom of sodium first. So these are the three shells of sodium. There's a positive nucleus in the center. There are two electrons over here. There are 8 electrons in the second shell, and there's 1 electron in the outermost shell. So I'm just giving an example of sodium. Uh, Now this electronic configuration is known as a ground state electronic configuration. What that means is that it's the lowest possible energy state of sodium. Now, in reality, the issue is that sodium goes into excited state. Sodium is absorbing energies. I mean, this is the lowest energy state for sodium's electrons. That the first 2 electrons are going to occupy the first shell, which is the lowest energy shell. Then 8 electrons would occupy the second shell, and then there's going to be 1 electron occupying the last shell. If the electron becomes energetic, it moves further and further away from the nucleus. So this electron over here is the most energetic because it can overcome the attractive forces of the nucleus, and it can stay very far from the nucleus. So the further they are from the nucleus, the energy levels keep on increasing for the electrons. If the electron has very less energy, it's going to be very close to the nucleus. It's going to occupy regions around the nucleus because it's not energetic. It can't overcome the attractive forces. If it can move to a higher energy level. Now, the point I'm trying to make is you have a lot of electromagnetic waves coming in from all directions, from the sun, from everywhere, from your phone, from your radio waves, infrared, etc. So there are all sorts of electromagnetic radiations that are coming in and that are striking the atom over here. Now, electromagnetic radiations are they contain all sorts of waves, radio waves, microwaves, infrared, ultraviolet, visible spectrum, gamma rays, x-rays. All sorts of radiations are present, all sorts of frequencies are present. Now, what could happen is that one of the electrons, let's pick this electron, might absorb a certain amount of energy from a particular frequency. And when it does that, it becomes energetic. When it becomes energetic, it moves to a higher energy shell or subshell because it has now gained energy. So it can now occupy spaces, the empty spaces, which are further away from the nucleus. So this is an example of excited state. Excited state is that electrons from lower energy states or lower energy shells, they gain energy, and move to higher energy shells. So the electrons over here, in your case, are not restricted. They can move around. They can jump up. They can move towards a high energy shell, or they can lose energy, and they can move to a lower energy shell. Uh, why? Because you have all these electrons that are all these electromagnetic radiations that are coming in, which are being absorbed by these electrons.